All right, let's jump right into this explainer and transform the periodic table from a static poster of random letters into a dynamic, logical map of scientific discovery. If you're a student of chemistry or honestly just someone fascinated by how the universe is put together, you've probably stared at this chart a million times. But today, we are going to look at it not as a list of stuff to memorize, but as the ultimate student study guide. It is literally a story of chemical chaos brought into perfect quantum order. Here's our exact roadmap for today's explainer. First, the quest for order. Then, the quantum plot twist. Next, mapping the elemental blocks. After that, naming the heaviest elements. And finally, decoding periodic chemical trends. Starting with Section 1, the quest for order. From chemical chaos to Mendeleev's genius. Okay, we're starting our detective story in the 1800s. Imagine being a chemist back then. You're basically drowning in a sea of unorganized data. By 1865, they had 63 known elements, with no real system. Now, let's trace the timeline of the early pattern matchers who tried to fix this, paving the way for Mendeleev's massive breakthrough using atomic weights. It kicked off in 1829 with Johann Dobereiner and his law of triads. He noticed groups of 3 elements had similar properties, right? And the middle one acted like a perfect average of the other 2. Then, in 1865, John Newlands proposed the law of octaves. He realized properties repeated every 8th element, literally like musical notes. But, well, Newland's logic kind of fell apart after calcium. It wasn't until 1869 that Dmitri Mendeleev organized the elements by increasing atomic weight, creating the foundational layout we all recognize today. But what's truly dramatic about Mendeleev is his sheer boldness. I mean, he literally left gaps in his table and successfully predicted the exact properties of missing elements. He figured out that if the order of atomic weights didn't align with the chemical properties, either the weights were wrong or an element was simply undiscovered. He actually left a gap under aluminum for an element he dubbed Eka aluminum, and sure enough, years later, gallium was discovered. Its properties, like its density and atomic weight, were almost identical to Mendeleev's calculations. It was an absolute triumph of scientific prediction. Moving to Section 2, the quantum plot twist, Moseley and the modern periodic law. As we move into the 20th century, the whole narrative shifts from atomic weight to the true hidden engine of the table, atomic numbers. The absolutely crucial point here is that atomic number, meaning the number of protons and electrons, dictates an element's electronic configuration and its exact place on the map. In 1913, physicist Henry Moseley shot X-rays at various elements and found a perfect mathematical straight line when he plotted frequencies against atomic number, not atomic weight. This completely flipped Mendeleev's initial classification logic on its head. It wasn't about how heavy an atom was, it was all about the fundamental charge sitting in its nucleus. And this is where modern quantum mechanics perfectly explains the physical structure of the table. The length of each row or period directly corresponds to successive electron shells being filled. The principal quantum number, known as n, defines the exact size of these energy shells and subshells. Take period 1. It only has 2 elements, hydrogen and helium, because that first shell can only hold 2 electrons. By the time we drop down to the 4th and 5th periods, the subshells expand, giving us 18 elements per row. It's just a beautiful way of bridging abstract quantum numbers with the actual physical layout of the elements. All right, Section 3, mapping the elemental blocks, the city neighborhoods of the periodic table. It really helps to treat the periodic table like a city map, divided into 4 highly distinct neighborhoods, known as the S, P, D, and F blocks. Your specific address in these blocks is entirely determined by the last orbital filled with an electron, giving each block very distinct chemical behaviors. The S block on the left contains highly reactive metals that form compounds used incredibly heavily in modern manufacturing. On the far right is the P block, housing your essential nonmetals and noble gases. But the true engine room of global manufacturing, that's the D block in the center. These transition metals act as critical chemical catalysts, driving massive, large-scale industrial reactions and creating the chemical energy modern factories rely on. And finally, tucked way down at the bottom, is the F block, housing the complex and often radioactive inner transition metals. If you sweep your eyes across this map, you see a really stark physical contrast, shifting from highly conductive metals on the left to brittle nonmetals on the top right. We can actually compare physical properties to show exactly how these blocks function in the real world. Metals make up roughly 78% of the table, featuring high melting points and serious malleability. But as you cross that distinct zigzag line of metalloids heading towards the P block, you hit the nonmetals, which are completely defined by low melting points and poor conductivity.
Modern industrial manufacturing literally relies on this specific spectrum of reactivity and physical hardiness to build everything around us.
Let's hit Section 4, naming the heaviest elements, the IUPAC decoder ring. So, for elements beyond atomic number 100, things got complicated. These are highly unstable, man-made synthetic elements, but the scientific prestige and the economic significance of securing the resulting tech patents is massive. Finding these elements expanded our entire understanding of atomic structure. During the Cold War, American and Soviet scientists actually had a huge dispute over who discovered element 104, which resulted in two entirely different names circulating at the exact same time. To stop the chaos, IUPAC devised a clever, systematic nomenclature using numerical roots derived directly from the atomic digits. Instead of fighting over names, any newly synthesized element gets a temporary name mathematically generated right from its atomic number. 0 is nil, 1 is un, 2 is bi, and so on.
Let's test this out like a proper study guide and see how we can decode the name for element 120 together. Just imagine a lab synthesizes this tomorrow. What do we officially call it before they get to vote on a permanent name?
It's super simple. Step 1, we take the root for 1, which is un. Step 2, the root for 2, which is b. Step 3, the root for 0, nil. And then we just slap the suffix isium right on the end. And boom, there we have it. Step by step, we just built the temporary name unbinalelium, completely demystifying the heavy element naming process. It is a perfectly logical system for a table built entirely on logic. Which brings us to Section 5, Decoding Periodic Chemical Trends, the Universal Laws of the Realm. For our final section, we're diving into the universal laws that allow you to predict the chemical behavior of practically anything. These specific reactivity trends are exactly why industries rely on the periodic table to build new chemical products. But here is a fascinating puzzle. If you are adding more electrons to an atom as you move right across a period, why does the atomic radius actually get smaller? It feels totally counterintuitive, right? More stuff should equal a bigger size. Well, the answer is that the growing positive charge in the nucleus outpaces the shielding effect. Shielding is just inner electrons blocking the pull of the nucleus. But because the new electrons are being added to the exact same outer shell, they don't really shield against each other very well. Meanwhile, you just keep adding more and more protons to the center. That massive, effective nuclear charge just yanks everything tighter together, pulling the entire electron cloud forcefully inward. And because those outer electrons are pulled tighter as we move right, the energy required to rip one away, which we call the ionization enthalpy, significantly increases. This right here is a massive predictor of chemical behavior for different groups. Elements on the far left give up their electrons easily. They have incredibly low ionization enthalpy. But try taking an electron from a halogen on the right side. No way. You are going to need a tremendous amount of energy. It's the exact same story for electronegativity. Pauling's electronegativity scale shows us that nonmetals on the right have a far stronger ability to just greedily attract shared electrons towards themselves. It goes hand in hand with the atomic radius. Smaller atoms with highly charged nuclei are incredibly good at pulling outside electrons in. Fluorine, sitting at the top right, is a perfect 4.0 on the scale. It is literally the ultimate electron thief. And this beautifully summarizes the overarching rules of the realm. Reactivity is highest at the extreme left, where metals readily lose electrons, and at the extreme right, where nonmetals aggressively gain them. As you go down a group, the atoms get larger and looser. As you go right across a period, they get smaller and greedier. This is your ultimate decoder ring. It explains exactly why we use transition metals for specific industrial catalysts, and why highly reactive S-block alkali metals have to be stored in oil just to prevent them from reacting violently with the moisture in the air. Which leaves us with this final crazy thought. As we push the extreme boundaries of physics to create entirely new synthetic elements, we already possess the map to predict their explosive secrets. Think about it. If element 121, unbiunium, is ever stabilized, it will sit extremely far down in the C block, or maybe even kick off an expanded block. Based on the universal trends we just decoded, its electrons will be so far away from the nucleus that its reactivity could be unlike anything we have ever seen. The periodic table isn't just history, folks. It's a very literal window into the future of matter. Thanks for diving into this explainer with me. Keep exploring and stay curious.